Let me welcome you all today to our webinar on high throughput synthesis of nanoporous thin films, a perspective on the accelerated discovery of novel energy materials. So we'll be starting in a few minutes. Let's give the others a couple of minutes to join. Meanwhile, if you don't mind, can you share your university name, your research topic, or just like a self-introduction in the chat so that we can interact better, if you don't mind? Hi, Shadi. All right, let's wait for the others. Just a couple of seconds. Okay, I guess everybody is on board. Let's move forward. Welcome again to today's webinar on high throughput synthesis of nanoporous thin films, a perspective on the accelerated discovery of novel energy materials. We have two speakers today, Professor John Gregoire, who's a research professor at Caltech, currently on leave from his position, and VSParticle CEO, Aaike Vugt. And I am Anagha. I'll be your host for the day. I currently work as the product manager for self-driving lab applications at VSParticle, and I have a background in high-throughput electrochemistry and electrocatalysis. So let me now briefly walk you through today's agenda. Yeah, so we'll start with an introduction about the company and then move on to speaker biography. And then we have our talks for today. The first one is given by Dr. John Gregoire about high throughput synthesis and characterization of metal oxide electrocatalysts. And then we have our second presenter, CEO, VSParticle, Aaike Vugt, about VSParticle technology and self-driving lab applications. And then we have our live Q&A session. So I want to let you all know that as and when you have your questions, please post them in the chat, along with whom you address the question to, and then we can dive right into those during our live Q&A. All right. Now, moving on about VSParticle. Yes, so we are a leading supplier of next generation tools for nanoparticle synthesis and deposition. We believe that high throughput experimentation underscores our mission to revolutionize the way materials are developed and manufactured. And we aim to create an impact in various industries like gas sensing, catalysis, and electrocatalysis. And more information about our technology and the research tools that we offer will come up in our CEO Aaike's presentation. So for now, let's move on to speaker biography. So we have two speakers, as I mentioned before. So our first speaker is Professor John Gregoire. I can for a fact say that John is a pioneer in the field of high throughput research because I've been deliberately following his work ever since my graduate years. It's truly an honor to have you here, John. Welcome. So John, as I mentioned, is a research professor at Caltech. He's currently on leave from his position. And he also works as the team lead for photoactive materials within the Liquid Sunlight Alliance, the US DOE Energy Innovation Hub. His team's primary objective is to accelerate material discovery by automating critical components of research workflows, utilizing combinatorial and high-throughput experimental techniques, and integrating them with materials theory and AI. We are extremely happy to have you here, John. Would you like to say hi to the audience, maybe?
Yes, hello. Thank you so much for the kind introduction and the invitation to be here today.
It's a pleasure. So our second speaker is, as I mentioned, VSParticle CEO, Aaike Vugt. Aaike is an extremely passionate and forward-thinking person who since a very young age was motivated by the mission of energy transition. With an in-depth understanding of the importance for scale and rapid innovation within the field of advanced materials, he co-founded VSParticle during his final year at the Delft University of Technology, with a clear mission of unlocking a century of material innovation in the next decade. We're so happy to have you here, Aaike. Would you
Thank
like
you.
to say hi to the audience? Yeah, okay. All right. So now, before we dive into our presentation, I would like to entice you with a question. So when it comes to material science, we are well aware of strategies like doping and alloying to improve the catalytic performance, right? And we've all probably dealt with bimetallic and trimetallic catalyst systems. So what I want to emphasize here today is the magnitude of new materials that lay waiting to be explored. So I'm going to give you a poll question right now. And in a minute, you will see the question appearing on the screen. Yes, there you go. So let's take, for example, a trimetallic system. Can you imagine the number of possible combinations that are to be considered if we were to vary the composition of each metal from 0 to 100% with an increment of 1%? Please feel free to go about with your guesses, or if you can do such a quick calculation, that's great as well. Let's see. Wow. Okay. So I guess you are in the right webinar, guys. But still, I'm going to just tell you what the answer is. So the correct answer is 5,151 possible combinations, much like you all guessed or you knew. So my question is, can you imagine going about testing so many compositions within like your research time frame, even if you were to use this traditional approach of step-by-step experimentation, where you go about testing and synthesizing each material one after the other? So it's impossible, right? So this is where the importance of high throughput experimentation and accelerated material discovery lies. I think now is the right time to step into our first presentation by Dr. John Gregoire. John, I leave the floor to you. Can you take control?
Yes, thank you so much. All right, well, with that extensive introduction, we can jump right in. I'll first say that the work is very much the product of an incredible team of scientists and engineers at Caltech. Pictured here in its kind of last fully staffed form. We've worked on a number of projects over 12 years at Caltech, a lot of them in the energy space, a lot of them using high throughput experiments, a lot of them using artificial intelligence and developing new algorithms. And the funnest part is tying all that stuff together. So we work in kind of a number of disciplines in the field and need different levels of characterization and theory support for our work. And so we have a large network of prominent collaborators that some of them will be highlighted in the results I'm showing today. To take a step back, and the introduction we just heard was kind of fantastic, and it really sets the stage for this kind of other view of the high-level view of the field. And it's from a perspective article wrote with Helge Stein a few years ago, and kind of envisioning a very notional but generalized learning cycle in experiments, particularly for materials and chemistry, where we have to plan things, synthesize, process, measure them, manage the data, and so forth. And said, well, look, what we're really doing in the field of accelerated materials discovery is applying a variety of techniques to augment or accelerate steps in this process. But when it comes to putting this in practice, it ends up looking a little bit different than this. So we kind of made some iconography of workflows, exemplars from the field that I won't go through in detail. But kind of looking at the trajectory of these, it kind of matches what we're seeing more broadly in the field of kind of 30-year overview of high throughput materials experiments in academia, kind of for basic research purposes, where the real rapid rise in use of kind of automation in experiments was right around the turn of the century, where we saw a big jump in the publication rate, and these were really focused on making very high throughput, often via parallelization experiments. Now, more recently, in the last several years, we've had a rapid rise in the advancement of autonomous-based systems, where we don't necessarily need parallelization, but we're kind of accelerating knowledge by making more prudent decisions that are usually AI guided about which experiments we should be running. In the future, one can imagine that, and we're already starting to see this, kind of integrating all the best practices from across decades of development. But we're still left with a question of why did we enter this kind of trough of disillusionment, as it is sometimes referred to, after this initial rise in excitement? And in my opinion, one way, and it's very much related to the excellent poll question we just saw, that's for 3-element systems, just 3 selection of elements. There's also a lot of different ways you can do experiments. And if you say for any given problem, there might be 1 billion experiments that you can perform in an exhaustive search. A lot of these examples for high throughput experiments said, we're accelerating research by a factor of 1,000, which is fantastic. But when the factor of 1,000 goes from 1 per day per 1,000 per day, and your funding cycle for research is like 2 or 3 years, you didn't get any much substantially further in doing the addressing the exhaustive billion experiments. And so we have a lot of work to go here in the future, and getting AI guidance to better navigate through these billion experiments, I think, is going to be really critical. And as we'll discuss, having the synthesis techniques that can automatically access those vast search spaces will also be critical. One final thing on this kind of high-level picture before we jump into some other specific experiments is that we're still not doing things in automation like human scientists do, right? Self-driving labs and high-throughput experiments look very different than just a lot of humans doing experiments. And that's because humans don't just choose what experiment to do next. They're doing this on-the-fly quality control using an extensive network of prior knowledge in their minds. Things like intuition that are hard to really encode in machine learning algorithms. And not only like choosing which experiment to do, but might see something surprising and just redesign the entire workflow to pursue a new line of inquiry. And so generation of lines of inquiry is something that we are very much not able to emulate in artificial intelligence the way humans do. So all that being said, there's been a lot of work in this automation landscape in the combinatorial material science community, automating and making very high throughput these kind of complex experimental workflows. But this scientific complexity axis, there's an ocean of opportunity here in which if we can get artificial intelligence to emulate and then eventually supersede the kind of reasoning and planning capabilities of humans, combined with this experiment level automation, there's really a lot we can do as a field. Okay, I'm switching now. This is not my work, but just wanted to show what's not high throughput synthesis to give you an idea of how fast the synthesis I'm about to show you really is. One of the pioneering techniques in combinatorial material science is these diffusion multiples, where you can put together blocks of pure elements and they interdiffuse into each other. A very complementary example, this is from a company, Wildcat, does battery research. They were using ball milling to do their synthesis for materials exploration. And it's one of my favorite examples of people ask, like, why is synthesis hard? Why can't we just predict what happens? This is titanium and graphite in a ball mill that after 66 hours of ball milling, all you see is the titanium, the reactant. After 82 hours, something magical happened and it all transformed to phase pure titanium carbide. And I don't know of any algorithms that were going to predict that that was going to happen. So this is all to say that synthesis as a broad landscape, especially in bulk form, can be very time consuming, and in all forms is very hard to predict. So how do we then say, all right, for my automated workflow or self-driving lab, well, what synthesis technique should I be using? Well, you'd be hard pressed to use that ball milling and achieve throughputs that can address the thousands in the poll question we saw to billions of experiments that may need to be done. So another perspective article we wrote to kind of evaluate this is to say, look, depending on what kind of automation and AI you're trying to incorporate, there might be a number of different metrics related to the speed, the scalability, the scope, and the quality of the synthesis that are important to you. And taking some prominent synthesis techniques from the field and scoring them against these metrics to see you get some very complementary shapes in these radar plots, meaning there are very complementary synthesis methods, and you have to kind of find the one that's right for you. The ones that we implemented in years at Caltech are inkjet printing and sputter deposition. I'm going to talk about the inkjet printing technique today. We coupled these with a host of different property screening measurements for both intrinsic kind of properties and performance properties, particularly focusing on the electrochemistry field. And we'll just see one example of that in a second here. So the inkjet printing occurs by dissolving elemental precursors such as metal nitrates or metal chlorides into a solution that can be printed by these modified Epson inkjet printers to print out these large arrays of dots where each one is programmed as a different color, which corresponds to a different composition, a different mixture of those elemental precursors. And the screening happens with this high throughput photoelectrochemical reactor. This has, for today's purposes, the light that's shining on and off is to do photochemistry. We're not going to be using the light today, but what we are going to be using is the flow pattern of this, that without a gasket, it has a continually flowing electrolyte that contacts 1 to 1.5 millimeters of working electrode area at a time. And we can raster that at will across to access different compositions in our composition libraries, such as that inkjet printed one we saw a couple slides ago. Okay, backing up to the kind of origins of this technique, but also it'll come back around in the end about where we think synthesis needs to go in this field, is that these ethanol-based inks where you can dissolve these metal precursors were really pioneered by the Galen Stuckey group at Santa Barbara and involve a number of components in this ink. Is a lot of them to promote solubility and stability and match the viscosity and surface tension needs of the printer, but also these structure directing agents that sometimes form these kind of micelles where they can organize the metal precursors so that when they get converted into metal oxides via calcination can form specific nanostructures. But depending on what the mixture of the inks is, sometimes that happens and sometimes doesn't. So you can get a variety of different kind of nanostructures out of your materials, but we don't have all the tools with which to control that explicitly, especially because the range of ink formulations we're allowed to use is very limited by the properties of the inkjet printer. But we can still make some things really fast. So the question, it's interesting, it's almost the same number. There's a little over 5,000 samples in this space. This is with 4 components, but instead of 1 atomic percent, it's 3 1/3 atomic percent intervals, right? So this is how we started searching high order composition spaces by taking 4 different elements from the periodic table, making their metal precursor inks, and printing them at all possible combinations at 3 1/3 atomic percent intervals. Now, additionally, then they get reacted with oxygen to form 4 metal oxides, or up to 4 metals at a time oxides. These many thousands of samples are laid out on this pattern with 1 millimeter square spots. After they go through the furnace, they come out looking like this, and then get passed on to that scanning electrochemical cell for measuring their electrochemical properties. I have 2 slides here just to note. I'm going to show you deep dive into the catalysis project, but we've used this technique to do a bunch of different approaches to accelerated materials discovery. This is an example for photoactive materials based on monoclinic bismuth vanadate, which is a prominent metal oxide photoanode, and which we are trying to co-dope, like substitute on multiple sites at a time in this material. For example, molybdenum on this axis and gadolinium on this axis. With the inkjet printer, we can combinatorially make all these high order compositions, and we saw lots of tuning in the structural, optical, and photoelectrochemical properties that I won't go into, but it's combining a lot of the structural characterization to get to the underlying science of what's happening in the materials chemistry in these high order composition spaces. A very different approach is a project we did with Google Accelerated Science, where we printed these continually varying composition lines that essentially were like a laser grid rastering through composition space. and by applying some models to that, could sometimes identify phase boundaries by changes in optical properties. More often, we found very useful is had a metric for essentially saying the probability that these elements are interacting in a way, like these three elements are interacting in a way that produces properties that are completely distinct from any one or two element combination. And so as we go to higher and higher order compositions, we don't need to make all the high order compositions. We only need to make the ones in which new chemistry happens. And so this is intended to be a high throughput detector for new chemistry in high order composition spaces. But for the data I'll focus on in the area of electrocatalysis, we printed these libraries as I described before. Whenever we get a kind of a hit, a catalyst that looks interesting in that library, we can take the same ink formulation and print a larger version. So we could go into a test bed electrolyzer and did a lot of validation of the high throughput techniques using this type of approach. Also print on rotating disk electrodes to perform more traditional and trustworthy electrochemistry, which also was really critical in validating all of our techniques to get this high throughput. The system that I'll focus on for the next few slides is using that 4-element combination as I described before for the printing. This is iron, nickel, cobalt in cerium. What I'm plotting here is a heat map of the overpotential, but here I'm taking a particular composition line that starts from a transition metal composition and cuts through the space to a 50% cerium composition. And if you ask, well, what's the best catalyst in this space? Well, it depends on what current density you're operating at, because at high current density, it's here. And at low current density, it's very much these cerium-rich compositions, which was surprising to us because cerium oxide by itself has no notable activity for oxygen evolution. And yeah, sorry, I forgot to mention this is in alkaline conditions, 1 molar sodium hydroxide. If we kind of look at this data in different ways, say, look, if you have single transition metals, you can add a second one and get a big jump down in overpotential, which is very desirable. If you add a third transition metals, you kind of at diminishing returns. But then if you add to the cerium, you can get another jump down again. And so this is an example of marching into high order composition spaces really gives you these emerging properties that we're looking for in materials discovery. So why is this? We tackled this for a number of years with a number of collaborators. It's a wealth of data, which I'm not going to go through in detail, but show you some of the kind of high-level results or to talk you through some of the high-level results. So the first one was kind of understanding the transition metal oxidation states and local coordination via X-ray spectroscopy with Junko Yano's group. We used this to kind of generalize some observations that we got from collaboration with Christian Kivalowski on atomic resolution TEM, which these were very radiation sensitive materials, so it was incredibly difficult measurements to get these atomic resolution images, which showed that everywhere we looked, while we have 4 metals in the system, they're not all in the same phase. The ceria segregates into these fluorite ceria particles and has these atomically sharp interfaces to these rock salt mixed transition metal oxide crystals. And so that's corroborated by kind of the composition maps and also that X-ray absorption study from the previous slide. Said, all right, well, if the cerium isn't being incorporated into this phase, how is it changing the overpotential so dramatically, particularly at low current densities? And to do that, we turn to looking at the initial oxidation of these materials in electrolyte with a series of in situ and operando XPS and XAS studies, which really corroborated what we started seeing in these high sweep rate cyclic voltammograms. I'm going to focus on this composition line that's similar to the one I showed you before, where if you start from transition metal oxides, you see a redox wave corresponding to, for example, like nickel 2 to nickel 3 oxidation at these kind of potentials, very corroborated with the onset of OER activity. But as you add the ceria, you can march down that redox potential by a sizable fraction of a volt. And the other part of that story is if you anneal these same printed materials at higher temperature, you destroy that kind of fine nanostructure. You grow the grains, and you have much less boundaries between the mixed metal oxide, transition metal oxide, and the fluoride ceria, and the improved overpotential low current density goes away. And so this is kind of showing us a successful implementation of high throughput techniques to screen a number of compositions in a high order composition space that would very much not be amenable by traditional means. And the inkjet printer is fantastic at doing that. But as I kind of alluded to in the ink formulations, we can discover interesting nanostructures, but we have very limited control over that nanostructure. We have to use the thermal processing required to kind of burn out all the components of the ink that we're not interested in and convert these to metal oxides. And sometimes in that one kind of composition we saw with 50% cerium and a mixture of transition metals, that provides a very optimal nanostructure as far as we know, but we have limited ability to kind of independently control composition, processing, and nanostructure. And so for that, we're really looking to a future of synthesis techniques where we can gain control of those various axes. And so we had a collaboration earlier this year that I'll show you a few slides of before turning it over to Aaike to tell you about this in much greater detail. So this has a platinum source, a nickel source, mixing them together so we can print mixed nickel platinum nanoparticles on a ITO coated glass plate, very similar to that inkjet printing glass that I showed you before. And this is done by controlling the power in the two elemental generators of nickel and platinum to control the composition, and then rastering a beam of nanoparticles depositing onto our substrate. And the rastering speed here can control the loading, nanoparticle loading, or the metal loading of our sample. And so we're then making an array of dots that are very intentionally analogous to that inkjet printing array so that we can use the same scanning droplet cell to measure the properties of these different dots. So the first thing we looked at was, we're also here going to look for oxygen reduction chemistry. The results I showed you previously from inkjet printing were oxygen evolution, but for starting with a binary metal nanoparticle system, we thought it would be a better validation study to look at acidic oxygen reduction. And initially, looking at these chronoamperometry measurements, we're seeing the expected trends, which were also mimicked in data I'll talk through a little bit more. These series of cyclic voltammograms where purple means it's platinum, yellow means it's nickel, and the width of the line corresponds to its metal loading, which we also varied in this library. And we're seeing a few features that look very promising to us in the ability for this synthesis tool to enable us to explore these kind of composition spaces. One is that we have a very early onset. This is much better than anything we've gotten from our other high throughput synthesis techniques, likely due to the very high surface area of these nanoparticle systems. And it could be also the preferential exposure of edge sites and other things. All to say, it's very well known that nanoparticle structures are optimal for oxygen reduction, particularly with platinum and platinum alloys. And we're seeing that kind of state-of-the-art performance with respect to onset potential in these films. Also, as you added nickel and dilute the platinum or lower platinum loading, the cathodic current density marches down as we expect. And an interesting feature is you may notice in the previous slide and in these, there's lots of waves. Those are waves from the peristaltic pump, right? That's the frequency of the peristaltic pump you're seeing, which changes the effective kind of flow rate near the surface. And these waves are apparent when we're in a diffusion limited regime, particularly because this is oxygen reduction and we have a limited supply of O2 to be reduced. But when you're in a catalyst kinetic limited regime, you don't see those oscillations because the local delivery of O2 is not limiting. And so all of this is kind of looking great, making sense, matching our expectations, and overall validating that we can use existing high throughput electrochemical screening techniques to rapidly explore these printed nanoparticle arrays. And so with that, I will turn it over to Aaike, or I don't know if we're doing something else first, but yeah, thank you very much for your attention.
Thanks a lot, John. That was truly inspiring. So before we move on to Aaike, I have to mention that it was really interesting to see that if you have the right tools, a lot of meaningful data can be generated. And the part about how nanostructuring impacts the catalytic performance was also very interesting to mention. Now, we have our next presentation by Aaike, but before that, so we heard about a lot of techniques, high throughput synthesis techniques like inkjet printing from John's presentation. So I have a quick question to you about what are the different techniques that you use for your research in your lab. So a poll question is coming up for you. Please cast your votes. Right, I see different. By the way, if you don't find the technique that you use in the options here, please do mention that in the chat. That would be great as well. Nice. Thank you. So there are some PVD, inkjet printing, and spark ablation users here as well, I guess. Okay, thank you guys. Thanks. That was insightful. Now, I think now is the time to move on to our next presentation by Aaike. Aaike, could you please take control?
Yes, I can. Before starting, of course, John, thanks a lot for giving this overview of the field that you have been very active in and you will maintain very active in, I believe. But thanks a lot for the great insights, and I think it gave a good introduction to my presentation. So, hi everybody. As you know, my name is Aaike van Vugt, co-founder and CEO of VSParticle, which we started off almost 10 years ago as a spin-off company from Delft University. So in my presentation, I would like to share 3 parts. So vision, mission of the company, nanoporous thin films, what they are and why they are so important, and our solution in this space. So as a company, we believe solutions for big issues are urgently needed. And of course, the most important crisis we are facing is the energy crisis or the climate crisis, where we need to decarbonize our society. And we do believe that materials, they play a very impactful role in changing this energy transition. We need new materials for batteries, solar cells, catalyst materials for green hydrogen production, and many more. We also believe that a very short time to market is needed for those materials, because most of those new materials are still in a development, or they still need to start the development phase. And since on average it takes 15 years to bring a new material from your first experimental test in the lab all the way to mass manufacturing, this is a timeline we don't have to create this energy shift. So we need to accelerate the development of new materials. So our promise is that everything we do at VSP is to contribute in one goal, unlocking a century of material innovation in the next decade. And that can only be done by changing the way we develop new materials at every step of the process. And high throughput experimentation, so high throughput synthesis and high throughput screening, is a very important step in that part. And as a company, we are fully focused at the moment on fast synthesis and easy printing of nanoporous materials, and especially nanoporous thin films. Because we see that it's a domain of materials that is very essential to a lot of energy applications, but it's also the domain that is most complicated. So from the, 2-3 decades of development in the semicon market, we have terrific technologies to make solid thin films like PVD, CVD, ALD, but we don't have a similar well-developed technology to make a nanoporous thin film. So again, why are nanoporous films so important? As mentioned, these very high surface area films, they play an essential role in some of the important applications like next generation gas sensors, next generation catalyst coated membranes. And then you can think about catalyst coated membranes for water electrolysis to produce green hydrogen, or CO2 electrolysis to convert CO2 into valuable chemicals, or nitrogen electrolysis is also a possibility. And all kinds of other high valuable chemical conversions that are being developed at the moment. As a third market, you see that nanoporous materials are very important in solid state type of energy storage. So again, a type of material that is of great essence to change our energy transition, and we need to become better in creating these materials faster. So this is the common problem we try to solve, this very long development timeline that is not matching the timelines we need for meet our Paris Agreement. So why does it take 15 years? Maybe a bit perspective on that side. I think partly it has already been covered by the talk of John, but there is no computer that can predict which material we need for a next generation fuel cell or a next generation battery. I know with generative AI and with all the computing capabilities we have today, computers are becoming better and better. But still, it's not to that point that you don't need to do, let's say, a trial and error material discovery process. So doing a design, build, test, learn cycle is the only thing that we can really do effectively. So that's what most material scientists are doing. And to find a breakthrough material, you need to do 100, maybe thousands of these cycles to test new materials to really find your breakthrough material. And knowing that a single cycle to make a new material, characterize it and test it could already take up weeks or months, you know that if you need to do 100 of them or 1,000 of them, you are already, let's say, 10 years down the line before you have really discovered your breakthrough material. And then scaling that material that really improves the performance of your final product could take another 5 years, because scaling from your lab process to industrial manufacturing is not an easy process. So at VSP, we have developed a new automated production process fully optimized for thin film nanoporous materials. So basically in our system, you put in rods of solid materials, you press a button, and then the system is breaking up the rods into these very small particles and directly printing them into a well-controlled, homogeneous, highly nanoporous thin film. And it's not only doing that on R&D scale, we are day in, day out actively developing our next generation technology to lay the foundation for our development tool and production tool. We are actively developing a production tool for catalyst-coated membranes for PEM water electrolysis, where we are initially fully focused on printing this nanoporous iridium layer 10 times lower than the current loading at high velocity. So this system will really be able to coat 15,000 square meters of substrate, either the membrane or the PTL, with this unique iridium coating. So we really know that this technology that we are using, spark ablation, is scalable and enables us to do also high volume production. So the last part, so maybe a bit more on the solution that we have developed to give a bit of background on the samples that we have made for John for this initial validation. So over the years, we have developed a solid portfolio of different products, starting off with the VSP G1 nanoparticle generator. And today I will focus on the VSP P1 nano printer. But please look at our website because there are products for different specific use cases. So the G1, which is basically our working horse at the moment, to convert these solid rods of material into these very small gas phase nanoparticles that we need to print these nanoporous layers. So in the G1, in the source, we use those solid rods, and in between we form a spark. With the spark, we go up in temperature to 20,000 degrees Celsius or higher by creating this plasma. So basically, we directly evaporate a small fraction of the electrodes. And out of this evaporated material, we condense, let's say, very small inorganic nanoparticles floating in the gas phase. This is a continuous process. Basically, every spark is a batch process. But if you do 300 or maybe a few thousand sparks per second, it feels like a continuous process of production of nanoparticles. The evaporated material is carried away with an inert gas. We use mostly argon or nitrogen, but you can play around with different gas compositions. Adding oxygen to the gas will help you oxidizing the nanoparticles very rapidly. So there are all kinds of things you can play with. The electrode configuration gives you a lot of capability to mix materials. So you can use 2 electrodes of the same material. So let's say silver and silver, then all particles are pure silver. If you have 1 electrode of silver and 1 of gold, then you will have particles of pure silver, particles of pure gold, and particles of anywhere in between. If you really want to control the stoichiometric mixture of the materials in each particle, you could use pre-alloyed electrodes. This could be pre-alloyed electrodes of binary, ternary, or any, let's say, combination that you are interested in. And we know that in the sparking process, the particles will have very close to the original composition that you used. By using multiple sources, for example, in the printer, you can use 2 of those nanoparticle sources. You can play around with all kinds of more complex structures that you can print. So there's a lot of flexibility already in that side. The other flexibility comes if you look into the materials that we can process. Again, we process the material using this plasma, this very high temperature plasma. And because of that, almost all solid materials at room temperature will evaporate at that temperature. So all the elements in green can be processed with the same system. You can process them in pure or any of those mixtures that I showed before. So moving on to the P1 nano printer, it's good to mention that the printer has room to house 2 of those nanoparticle sources. You can equip them with different elements, and then you can mix the output of the sources before printing. So if you buy initially the G1 to do some small-scale tests of our technology, you could always later on upgrade your system to the printer if you want to do more advanced type of material synthesis. Next to the sources, there is a stage on which you can apply your substrate, which has XYZ control. And inside this chamber where the stage is, we operate at a lower pressure to basically impact the particles onto the support. In the stage, there are also 2 camera modules to verify what you have been printed, but also to align the stage to the right starting position. So the printing process is by creating a big temperature or pressure difference upstream and downstream. Upstream, so coming from the nanoparticle source, is roughly at 1 atmosphere, or downstream we have this raw vacuum. It's 0.2 millibars, and because of this pressure difference and a small nozzle, we get the acceleration of the gas flow almost to supersonic speed, which helps us to impact the nanoparticles on this 2D substrate. So basically, you just have a printing nozzle that you can control XYZ to print any pattern that you need. The spot size that you can print is, let's say, 100 microns or thicker, but can be tweaked to your specific desires. The printing stage is at the moment, I would say, 12 by 12 centimeters effective printing. So you can go to relatively big substrates already in this R&D printer. So one of the benefits is that you can make these patterns. So you can make these arrays of samples in a single fully automated script. And they can all be the same composition. They can be different compositions and also different porosities. So the nice thing is that you can program the printer with scripts to change the printing time, to change the printing conditions, to change the porosity, but you can also change the output of the 2 sources to change the elemental composition from spot to spot. And this really opens up new capabilities, both into this nanoparticle-based nanoporous thin films, but also into the field of high-throughput self-driving labs. The nice thing about this 3-phase process, so the first phase is converting the bulk with these high temperature plasmas into nanoparticles. Then we can measure if it's needed. We could measure the particles in line, and then in the last step, we print them. There's already all kinds of capabilities we can add to do inline quality control so that you really know exactly what the material is that you are printing. Last, the example that also John showed. So if you use 2 sources, 2 G1s in the printer, One source can make process material that is green, the other one can process the red material into nanoparticles. Both nanoparticle streams are then combined into a single stream, and that is then being printed. So what you print is a nanoporous layer that is built up of green nanoparticles and red nanoparticles. But the nice thing about the fact that those particles are so small, 2-3 nanometer in size, is that they have very fast alloying kinetics, again, if the material will form an alloy. So at post-annealing, you could make this composite material into an alloyed material because of this phenomena that you will form rapid alloys with these very small nanoparticles. One additional comment I would like to make is that we can print these nanoporous layers on almost any substrate. And the reason is that we print or we build up these layers by using very small 2-3 nanometer particles, which by themselves have a very strong van der Waals force. And this strong van der Waals force will make them stick to anything, to any surface, but also to any of the other nanoparticles that you print. So we can print these nanoporous layers directly onto polymeric membranes, onto silicon wafers, onto copper foils, onto glassy carbon substrates, onto rotating disc electrodes. So that makes the process not only very material flexible, but also substrate flexible. In the case of John, we printed on these ITO-coated glass plates. So last, I would like to mention that the printer is being analyzed by some of the top groups, both in Europe and the US, including the Caltech group, to evaluate as a next step material synthesis for high throughput self-driving lab applications. Again, because of the huge material space, because of all the inline quality control, we have very high reproducibility, much higher than any wet chemical method, high level of automation, because we are not limited by chemistry. So if you want to change the elemental ratio between two materials, you can just change them by changing the frequencies of the two sources. It's not a matter of chemistry, whether or not it will work. And it's very fast and scalable. So using the P1 for your high throughput lab and knowing that we are developing already the industrial production system means that you could scale up any material that you discover very quickly to mass manufacture. So again, our goal is to bring this 15-year timeline back to just 1 year and create the right materials or enable the material community to bring the required materials into the market in the coming, let's say, decade to solve this climate crisis in time. So thank you. And I think now we are going back to Aaike for the last part.
Thanks a lot, Aaike. That was very insightful with regard to the urgency of moving to accelerated material discovery. And I hope that you all are now a little bit more familiar with the VSParticle technology and its potential. Now, I know that you're all eagerly waiting for the Q&A. Please also start posting the questions in the chat with whoever the question is addressed to. But before that, I have a quick question to you, the last one for today. So we have heard a lot of aspects of accelerated material discovery and high throughput approach today. So I think it would be nice to touch upon the challenges that you face when you use these approaches in the lab or you work with them. So there is a poll question coming up on the screen right now. So I want you to vote for the most frustrating challenge that you face when you deal with this in your lab. And again, if you have something else that's not in the options, please do mention that in the chat. Yeah, I guess they're all equally frustrating from the responses. Yeah, I also agree that reproducibility is probably one of the most important topics that could basically be addressed in itself. So this could be another webinar topic maybe. So if you guys have any other ideas as well for something else that you would like to hear from us, please also mention that in the chat. That would be very great. So we will now move to the Q&A. But before that, I have a quick announcement. So we have this survey about state-of-the-art thin film technologies. It's a performance assessment survey. So what we aim to do here is to get insights from experts like you about the performance of these thin film technologies. So what you would be asked to do is to select the technology that you're most familiar with and to rate that against certain performance metrics. So you can actually find the link in the chat right now, and we will also forward this link along with the recording of the webinar later via email. So if you have the time, we would really appreciate your participation, and you also get a chance to win a €50 gift card. Okay, so now let's move to the live Q&A. I will start reading out the questions from the chat because I guess that we already have some questions. Yes. So Amin has a question. Thanks for your interesting talk. I've previously worked with this technique and have two questions. First, how can the particle size distribution be controlled? And second, considering this is a non-equilibrium process, do you think it is possible to overcome the immiscibility of elements? I think this question is addressed to Aaike.
It's a very good question. So in the current status of the technology development, I would not focus too much on changing particle size. So since we are focusing on, let's say, printing thin film nanoporous layers, we see that most particles become, let's say, stable. We call them primary particle size at 2-3 nanometer in size. And that are basically the building blocks that you use to build up this porous thin film. And by using those particles, you can create the most porous thin film that you can create on Earth, I would say. So there will be capabilities, I would say, in the coming years to really tweak the particle size and make them bigger or smaller. We know that can be done. But for the coming period, let's say, if you are considering to adopt the technology on the short term, just focus on using the printer to create this very nanoporous material. I think just by using those very small particles as they come out of the process themselves without any optimization or tweaking, you can already make a big step forward in creating thin film nanoporous materials. And the other part about whether or not they form alloys, that's something most of our customers are verifying by doing the post-annealing, then doing the XRD analysis to verify if there are new patterns coming up. Those that you would expect from an alloy compared to the, let's say, composite material.
Thanks, Aaike. So the next question is by Hannah to John. Did you try making the composition gradients containing cerium also by sputtering? Did it change the activity versus the inkjet printed gradients?
Yeah, that's a good question. That's testing my memory. And the answer is a bit. We did some of the compositions with sputtering, but accessing those continuous variations of 4 components is just very difficult from sputtering. So techniques where you can mix the different channels, such as inkjet printing or the P1, are much more amenable to accessing those high-order composition spaces. When we did investigate the sputtered version of those films, we were actually already in a stage where we weren't doing OER catalyst discovery anymore. We were doing photoanode OER catalyst integration. And we saw some very interesting beneficial role of the cerium based on surface passivation of bismuth vanadate defects, which probably superseded its role in changing the redox potential of the transition metal oxide. So yeah, there's consistency in results, but really we were seeing studying different things and seeing different results in the sputtered films compared to the inkjet printed ones.
Thank you. And Hannah also has a question to Aaike. Can the sample be heated and is it limited to metals?
So there is currently no heating capability of the stage. That's definitely something we are considering. The sample can always taken out, put into an oven, if that is the question. I just want to mention that when you are printing the material, the gas is almost at room temperature. So there's almost no elevated temperature upon printing. Again, the spark is at very high temperatures, but already the moment the nanoparticles are exiting the nanoparticle source, the temperature is already down at room temperature because of the continuous inflow of carrier gas at room temperature.
Okay. Thanks. There's another question to Aaike. Thank you for your talk. During deposition through impaction in the P1, only a percentage of the nanoparticles ablated actually deposit onto the surface, while the rest run through the exhaust. Is that correct? And then that being said, you mentioned that you hope the P1 can deposit iridium with a lower loadings that show similar performance to the state of the art. Is the cost of the raw iridium electrode worth the lost material, assuming you're trying to achieve a more cost-effective CCM or catalyst layer?
Yeah, so all good questions. Let me come to them one by one. So the P1, the R&D system is not designed for, let's say, optimal use of materials. It's designed for flexibility and speed in mind. So what we see is that the deposition efficiency is, of course, very dependent on the parameters that you use. But we see that with some parameters, you can really achieve very high deposition efficiencies. I would say up to even beyond 90% deposition efficiencies. If you compare that to spray coating, which is much less efficient, there you see that maybe a 50% deposition efficiency can be achieved. So there you lose a lot of the material while the spraying process is going on. For the industrial system, the production tool that we are developing, there the utilization of the iridium rods is one of the highest priorities. And there we are aiming on a 80% utilization. So 80% of the iridium rods you put into the system will be converted into a valuable nanoporous layer onto your support. And the other 20% should be easily recoverable or recyclable.
Yes, the next question. Can the high temperatures generated during the spark ablation process lead to unwanted phase changes or chemical reactions that alter the desired properties of nanoparticles?
That could definitely happen. So there's no button on the printer which gives you control over, let's say, crystallinity of the final particles. In most cases, we see that the particles are so small that they are still some kind of amorphous. We see that by doing post annealing, you can change the crystallinity quite effectively. Of course, if you introduce oxygen into the carrier gas, both in the plasma, but also downstream, you will see that those very small 2-3 nanometer particles, they oxidize very rapidly if they oxidize as a material, which is less the case for, let's say, precious metals like gold and silver. But if you use, for example, other materials, that could happen. But if you use an inert gas that is very clean and you try to work as clean as possible, we have seen that we could even print copper where you have limited oxidation in the final material. So you can really print metallic copper with the printer.
Okay. Can sparked metal react with carrier gas such as nitrogen or CO2?
Yes. It's not a field that we have explored thoroughly as a company. We are, again, primarily focused on developing the tools to make them as easy and as flexible as possible to help the field forward. But we have seen different results where people have been using, let's say, reactive carrier gases to mix in carbon materials or nitrogen materials into the final sparked materials.
Hi, Andrew. I'm sorry if I'm pronouncing your name wrong. She asked a question. What is the temperature range used by the machine?
So at the spark, the temperature is, as mentioned, higher than 20,000 degrees Celsius. But for the rest of the machine, it's at room temperature. Okay. So the printing also happens at room temperature.
Yeah. And this is the last question. I'm sorry if some of your questions are unanswered, but due to the time limit, I'm going to the last question now. Can all materials be efficiently ablated using the spark ablation process, or do some materials have low ablation efficiency or produce undesirable byproducts?
We haven't seen undesirable byproducts, but there is a variation in the ablation quantity from material to material. That's partly due to the evaporation enthalpy of the material. But the nice thing is that the general process, so the 3 steps to convert bulk into nanoparticles, transport them and print them, that all works the same for all materials. You only need to change your, let's say, recipe or algorithm a bit to accommodate the difference in output. But that's a bit similar to PVD technologies, where you also need to do a calibration run to see the deposition speed before you will do the final sample.
Thank you, Aaike, and thank you, John. And like that, we come to the end of this session. The chat is still open, so please post if you have any further questions, please post that in the chat. And if some of your questions have been unanswered, please also feel free to reach out to us. I want to especially thank Aaike and John for their time and effort. And thanks to all the participants for your interaction and for your participation. Please feel free to reach out to us in the email that's provided. And also for more information, check out the website. Hoping to see you soon in the next webinar then. Thanks a lot for hanging in.
Thanks, Annika, and thanks, John. Bye, everybody.
Bye.